The first entry into a subject is the most important. But students in a science class are often greeted with technical terms, cryptic notations, and unpleasant formulas to solve for X. Certainly not the right start. The question is, how and where do we start? Let's begin with the how. What if we could begin by sowing the seeds of curiosity in these young minds? For instance, in a physics class, let students first have the chance to talk and express. We can put a question to them, such as, is force and energy the same? Their answers will be based on everyday ideas about these terms. They'll get some right and some wrong, and will even make us, the teachers, revisit our own ideas. What follows then can be a collaborative effort between the students and teachers, allowing the concepts to now sprout with strong roots. And needless to say, we'll clear some of our own misconceptions. This is as opposed to a method where students are directly told what everything is, and topped up with make-believe ideas, props, and wrong analogies to implant the ideas into those young minds on whom we are betting our own futures. Repeated reading, listening, and watching just leads to familiarity, but without these implanted ideas developing firm roots. Over time, more weakly rooted ideas pile up, and when students start jostling with them, we accuse them of overthinking. So now that answers the how. Give them the cues and allow them to come up with the answers. What about where to start? The clue lies in the most vexing question that students have. Where did all this come from? The short answer is, in the history of science, in our scientific discoveries and achievements over the past 5,000 years. The long answer follows. But before that, a little bit about me and the program. Dear parents and students, I'm Dr. Joseph, Chief Architect and Mentor of Katalyst. This unique program is aimed at students from classes 6 to 9, with the goal of giving them a strong foundational start in maths and science, and is organized into 4 modules, in keeping with the how and the where. Module 1 and 2 is our journey in time and answers the question of where all these ideas came from. Module 3 is dedicated to developing mathematical skills, what I like to call the mathematical toolbox. In Module 4, we look at physics. First independently of the maths, and then the maths. But not how to do the maths, rather why. Why those extra steps? What additional information are we getting? And then in conclusion, which is the most exciting part, we'll see all what has been learned through the engineering lens. Now let's see them one by one. Module 1 is titled The Creation Story and has 2 parts. Part 1 starts with the Big Bang, exploring the formation of matter from energy, the emergence of the 4 fundamental forces, and how they interact to form stars and galaxies, providing students with a seamless entry into the atomic sciences, which forms the foundation of chemistry and modern physics. Part 2 looks at the solar system and Earth, and considers larger questions first, such as why does the Earth have an iron core? And why not the outer planets? Why are they made of hydrogen and helium instead? We then look at our planet's history from its violent beginnings to the blue habitable planet that sustains life, and then embark on a journey from the core of the Earth to the continental crust, demystify the oceans, and then travel through every layer of the atmosphere and understand its importance in enabling technologies and in providing a climate that sustains life. This module is expected to generate interest in the environmental sciences as well, as the biggest challenge facing humanity today is to undo the damages that we have done to our environment, especially in the last 100 years. In Module 2, we focus on the last 5,000 years of human scientific achievements. This is where we'll get most of the answers to where did all this come from question. This era can be categorized into 5 phases. Phase 1 was heralded by the advent of agriculture, pottery, and metallurgy. Some early practical mathematics, followed by rapid strides in automation and structural engineering initiated by the Greeks and Romans, and early sailors who sailed for trade and conquest. Second phase, ushered in by Newton, Kepler and Galileo, demystified motion and formed the bedrock of three distinct engineering fields, namely aerospace, mechanical and civil. Third phase, led by Faraday, Ampere and Maxwell, unraveled electricity and magnetism that led to the lighting up of our cities, powered our factories, and revolutionized communication. Third phase also saw the advancements in the field of chemistry and set up the field of chemical engineering. With the fourth phase starting in the 1900s, man broke the deepest frontiers of science, looking into the depths of atoms. The insights from these developments answered some of the most fundamental questions about the universe. Many questions are still unanswered and will be answered by the coming generations. That's 5,000 years of scientific history summarized in a single frame. This is an example of concept map and will be one of the defining features of this program, integrating concepts into a single page and showing their interrelationships. We follow a similar trail in the history of maths. Starting around 5,000 years ago, man made some rapid strides in mathematics, championed by the Babylonian and Egyptian civilizations. They gave us basic arithmetic and geometry. The Greeks then unraveled the fundamental principles underlying all of mathematics. Achievements of Pythagoras and Euclid in the field of geometry laid down the template for many mathematical disciplines to follow. The work of Arab and Indian mathematicians made mathematics more accessible for daily applications. The epicenter then shifted to the West, that saw the rise of disciplines upon which our age of computers depends. This is another representation of the history of mathematics, as a tree with two main branches, pure and applied. This better represents the interrelationships between the various disciplines of maths. Both the approaches are adopted in this program and will go hand in hand. So while we follow the chronological approach, we will also be adding the various disciplines as branches to the tree of mathematics. Now make no mistake, this module is not a mere narration of scientific achievements. Several student exercises within this module are designed to replicate the discoveries of these early scientists like Kepler, Galileo and Newton, by doing the exact same experiments and mathematical deductions that they did. This will be a proud moment for the students, as these ideas and discoveries will now be their own. They will leave this module with a clear understanding of the scientific and mathematical methods. They would have understood the context in which the laws, definitions, and formulas arose, but will still have some unanswered questions, which will be answered in modules 3 and 4. Module 3 lays down a 3-step approach to problem solving in general and goes by the acronym EAR, where E here stands for the entry step and is indicated by the pause button. This is the most important step and is often missed by students. Attack is where you attempt to solve the problem and is indicated by the play button. Certainly not the place where the action begins, but is the case for many students. Such an approach can help get quick answers to simple problems, but will not work for more complex problems, and the confidence will be short-lived. R stands for the review and aptly indicated by the rewind button, where you revisit the key moments of success and failure encountered in solving the problem. Majority of the students go directly to the second step and entirely miss the first and third. There is emphasis on this 3-step blueprint throughout Module 3, which is aimed at methodically developing the mathematical toolbox without any prerequisite knowledge. Let's look at some examples of the problems covered in this module. We start with an example of trading, the very reason mathematics started. This challenge deals with discount and taxation and the order in which it is applied to the MRP. The insights gained will help the students develop an intuitive understanding of the order of operations. Additionally, they will develop an insight into the workings of a supply chain. Next will be an initiation into formulas. Students will be tasked with sequentially folding a paper strip into halves, recording the results in tabular form, and then making a predictive formula that relates the number of folds to the flanges. This exercise will help students to understand and look for maths in the simplest of things around them. The next challenge initiates the students into mathematical modeling. Students will be encouraged to take multiple approaches to solve the problem, as each approach is expected to reveal a different aspect of the problem. One of those approaches will be mathematical modeling. A challenge titled Little Cardiologist is aimed at getting young minds to appreciate the potential of data science. Students will be given the 3 angiography reports, then tasked with scoring the disease severity in an objective manner, and then recommend among the 3 treatment options available, namely bypass, stent, or medicines. Caution here, cardiology is much beyond this challenge, but the purpose here is to show how mathematics has permeated every branch of science and is decreasing ambiguity and blunting judgmental errors. A challenge titled Little Architect is aimed at initiating students into engineering design. Students will be guided to draw a floor plan for their dream home using simple geometric techniques, followed by estimating the cost of construction. They will later get an opportunity to modify this plan based on concepts that they will learn in physics. A total of 20 such exercises in this module will help students develop a comprehensive mathematical toolbox. What do I mean by that? Consider a problem that needs mathematical analysis, a branch of mathematics that deals with continuous variables. Our next task would be to ascertain the degree of accuracy required for the problem at hand. If an approximation will do, then we'll solve the problem using the discipline of numerical analysis. On the other hand, if a high degree of accuracy is demanded, then we'll adopt the analytical methods, which includes the disciplines like calculus and linear algebra. With a reasonably good understanding of mathematics, we now enter the module on physics. It is divided into 2 parts. First part deals with the basic science and focuses on developing a strong theoretical understanding of concepts. The second part will look at the engineering applications of these scientific concepts. The basic concept section will once again draw upon laws, definitions, and formulas. And this far into the course, students will have an idea of where they come from. But the formulas that describe the physical phenomena are actually telling us a story. The question is, can we understand the meaning of all of them? Or will we be lost in the maths? I guess the answer is obvious. Let me cite an example. Take the case of projectile motion as depicted in the graphic below. 2 separate equations describing motion along the x and y axis with respect to time can adequately explain the motion. But students are often encouraged to go a step further and substitute for time in the second equation, which leads to a third equation. That seems a little complex. Most students don't understand the reason for this complicated step. All they know is if they miss it, then 2 marks will be deducted. But in fact, the actual reason for doing this final step is because the equation obtained tells us a very important facet of the motion that is not apparent from the first 2 equations. So this is the approach that we take in part 1. We try to understand the stories behind the equations. What are they telling us about the real world? The maths then will be seen as an enabling tool rather than a hindrance to understanding. Now let's look at the individual sections. Section 1 deals with motion on a macroscopic scale. In section 2, we study a special case of motion where there is periodicity. Section 3 focuses on heat and temperature. Section 4 looks at 2 unique manifestations, namely electricity and magnetism, resulting from the acceleration of charged particles, and will be first studied independently of each other and then unified. Section 5 deals with the properties of light, its interaction with matter, and its detection using instruments. The final section is on the properties of matter at the atomic and subatomic scale. Part 2 is the application of physics to the engineering world. We begin with the application of Newtonian mechanics and thermodynamics to aerospace applications. Start by estimating the safe landing length of a runway for a passenger aircraft. Then we rescue a nose-diving fighter aircraft. Next, we deftly dock a space shuttle with the International Space Station. And finally, simulate a travel plan to put a rocket into orbit around the moon. In the next challenge, we look at structures in general and focus on structural elements, how it carries load, and analyze its load worthiness with the help of Newtonian mechanics. We analyze the Golden Gate Bridge and also design a bridge from scratch with a price cap. This exercise is intended to give students an idea about civil engineering, design, and town planning. Next challenge focuses on mechanisms and power transmissions, which are at the heart of all machines. As a case study, we'll see how it applies to automobiles. This exercise brings out the interdisciplinary nature of science and engineering by drawing on ideas from the first 4 sections. We then understand various sources of energy and energy balance, and how we maintain temperature in our homes, and how these considerations, when factored into the final structural design, can lead to cost savings and, more importantly, reducing the carbon footprint. Next is the application of electromagnetism and optical technology that has led to the communication revolution. We begin with a study of the first ever telephone and then follow the evolution of mobile technology from the age of 1G to 5G. The concluding section has 2 challenges. In the first challenge, students will estimate and design power requirements of a small town and draw up a plan from power generation to transmission. In part 2, students will draw the circuit design for their dream home based on unique power requirements of various rooms. This will sum up all that has been learned in sections 3 and 4. To sum up, the highlights of this program. 1. Answering the question of where all the ideas came from by learning things in a historical context and discovering many of the ideas firsthand. 2. Integrating a wide array of concepts and ideas into concept maps. 3. Assembling a mathematical toolbox. 4. Understanding the scientific method. 5. Learning physics by going beyond the maths and looking into the deeper meanings that the equations are trying to convey. 6. Applying the maths and physics to the real world. The end of this course is a new beginning with students now having a good understanding of the various disciplines of science and engineering and the transdisciplinary nature when it comes to applications. Also, a clear appreciation of the avenues and revenues will allow students to entertain more career choices than the traditional 3 or 4. The approach should help to decouple education from the stress of competition, freeing up education to serve as a tool for empowerment. In addition to the immediate goals of getting a head start for competitive exams and making more informed career choices, the broader goal that this program enshrines is to make a tectonic shift from a mindset of 9-to-5 jobs where you methodically grow your career and portfolio to a generation that chooses to be adventurous and autonomous in their career plans and sees themselves in a larger role as custodians of the planet, who don't ask the answers but take ownership to provide solutions for the challenges of tomorrow. So what's in the name Katalyst? Students' ownership of knowledge. That's where the K comes from. Because most of what they learn will be by discovering it for themselves. Greater application. That's where the A comes from. Of what they have learned, thanks to the concept map approach that will be adopted in the program so that they will know how to put the ideas and concepts together into an application. And as a result, a complete realization of their talents and potentials. That's where the T comes from. Dear parents, if what you've just heard from me is your vision for your children, then kindly express your interest via WhatsApp on 86-528-18745 with the following details. My message to teachers and heads of schools who share the same values and goals. If you feel that I could be of added value, then please feel free to contact me on the same number or write to me at my email is as follows. It'll be my honor and privilege to collaborate with all of you. To all the young minds out there, I'm looking forward to meeting the restless learners inside you. This program is set to begin in the first week of December. Further details will be posted. Till then, be nice, stay curious, and do dream as to how you can shape a better future for all of humanity. Thank you.